All right, so with the volume of revolution, what we're trying to do is we are taking a shape. Now we need to first understand what we're going to be moving into the three-dimensional scenarios here. We're going to be dealing with 3D objects. This is volume, obviously, is 3D. And what we're going to be doing is we're going to be taking a shape, taking a curve, for example, and this is my y, my x, and my z axes. Okay? And what I'm going to do is I'm going to take the area under that curve, and I'm going to take that area and I'm going to spin it around the x-axis, and it's going to create a volume. Okay? An easier way for me to try and do this than draw it, because this does require some pretty good artistic skills, of which I am lacking. GeoGebra does a pretty good job of doing this for us. I've graphed the curve 4 minus x squared. Okay? 4 minus x squared from 0 to 2, only in the first quadrant. Okay? And when I take this, and so on the left pane, it's just dealing with the xy axis. But on the right pane, you see that I've got a z-axis in there now. Now what I'm going to do is I'm going to use the x-axis as an axis of revolution. Okay? Now, imagine, you tell me, what is this going to look like once it's been spun around the axis? What's it going to look like? Yeah, it almost looks like a frisbee, right? Or like the cap of a wide mushroom, something like that. Okay. Okay. And let's see it. Kind of neat. Yeah, in certain applications, absolutely. All right. Okay. So what we're going to be doing is we're going to be trying to find the volume of that object. Okay. So first of all, let's apply it to this picture here in kind of a general form. Now remember, when we were doing the area under the curve, we started off by talking about the Riemann sum. We talked about a little tiny rectangle, and that rectangle got narrower and narrower and narrower, and we had more and more rectangles until we had a really good approximation of the actual area under the curve. That was the process we used, right? Okay, well, we're gonna start with that idea because it works. And we're gonna start by saying, okay, let's have a general looking rectangle. Right? Now, if I take that rectangle and I spin the rectangle around the axis, what do I get? Not a circle, because remember, it's got a width. What would it look like? It would look like a cylinder. It would look like a very narrow, a very thin cylinder, like a disc, right? Like a coin or a disc. Okay. It would probably look. Lousy artist here. Yeah, that's what it would look like. It would be spun around the axis to look like a disk. See? So the volume of that disk is made, well, first of all, we need the equation of the volume of a cylinder. We all remember that one, right? Yes, very good. Pi r squared h. Okay, now let's look at that in terms of this image. First of all, what is the radius of that disk? We find that radius of the disk. What is that? Yeah, it's the height of the function right there, isn't it? Whatever that value is. So my radius is now going to be the function at some specific value, which we'll deal with later. But we're going to square it because it's radius. Radius is squared. And now the height of that disk is, now normally we're looking at a cylinder in this context, right? And this would be the height, wouldn't it, under normal circumstances? But now we're not talking about a long, thin cylinder. We're talking about a short, fat cylinder that is, relatively thin. That height is this. That width right there, right? The width of that disk. See? Okay. So when we were talking about this in terms of a Riemann sum, what did we call that? It was a variable that we used. Delta x, right? That was my delta x. So the volume of that individual disk is pi, the function squared, times delta x. So if we were to use this idea with a Riemann sum, we now would just add up all the disks, and we would get an approximation for the value of the volume. Make sense? Okay. It's kind of like just a small twist away from what we already have done with Riemann. Okay. So now, when we did the Riemann sum, we went ahead and did the sum of all of the individual disks, or all the individual boxes, but now we're dealing with, that would be the sum if we were doing the Riemann approximations. But when we took the limit, and the boxes got narrower and narrower and narrower, in this case my disks are getting narrower and narrower and narrower, what did the summation approach? What new pentangled thing did we use for it? The integral. Good. That whole thing that the class is based upon. I'm glad all of us are really doing well at it. Now, instead of delta x, what did we write? Yes. And we can pull that pi out. And we would have to have some appropriate bounds. Okay, so if my bounds were going from A to B, my bounds now are A to B. So what we do to find the volume of revolution is pretty straightforward. We take whatever function we're talking about under whatever bounds. We square the function, integrate, and then multiply by pi, and then we're done. So in the example that I used a moment before, where I had 4 minus x squared we wanted to spin this guy around the x-axis, as the illustration did, and we're going to try and find that volume. So first we have to care about our bounds. Well, we can begin to set up our integral. We know we've got a pi out in front. What are my bounds going to be? Let's do that first. What's my left bound? 0. What's my right bound? 2. And now we take the function and we square it, and then we integrate it. So take a second now and evaluate that integral. We'll pause for a commercial break. So first, you expand your integral, you integrate, and then you apply the bounds. At the end, don't forget a common denominator, and don't forget the pi. A lot of kids forget the pi. Okay? Very often, especially on my tests and things like that, you can just leave it in terms of pi. You don't have to multiply the pi out. Okay? How are we feeling on that? Difficult? Impossible? No one ever seen it before? Of course I get, but not too bad, I hope. Right? All we're really doing is the same kind of integral stuff, but we're just squaring the function first and doing it in some, I mean, all the process is still the same. Okay? Are we all right? Okay. So, now, I'm going to stick with that same example. I'm going to abuse it as much as I can to get as much information out of it. And what we're going to do is we're going to now talk about the area of the volume of revolution between two curves. Okay? All right. So let's do the same. Four minus x squared, and then my other function is going to be y equals x minus 2 squared. We're talking about the area of that sliver between them. Almost the shape of what is called a digon. Okay, like the iris of a cat, or something like that. Okay? So, like before, we're considering the upper function and the lower function. Okay? But here's the way I want you to look at this first. There's a common error that occurs, and if you think about it the right way, you'll avoid it. What I've really got going on here, and I'm going to try and do my best at this artwork, but it's not going to be too great. I've got this outer shell that we saw in red on the GeoGebra, right? Now, what we're really doing is we're taking that mushroom shape and we're carving out this area, this volume now, underneath it. Okay? So if you were maybe if you were actually making this shape, okay, you could, put it on a lathe, make the outer shape first, make that mushroom cap, and then bore out the negative region on the interior, okay? And that's the way you should do it. Because your other volume, looks like that on the inside. See what I mean? And we're going to carve that out. So what we're first going to do is we're going to take this function and we're going to square it, and we're going to find that volume. And then we're going to take this volume and we're going to subtract it. Okay. Okay. And if we do this as two separate actions, you'll avoid a mistake that often pops up, which is sometimes kids want to mush it all together into a single integral, and then you wind up getting the wrong thing. So to do this as two separate problems and then subtract them, you'll be in good shape. So what I want you to do, and I don't want you to compute it, I just want you to set up the integrals. What I want to see is an integral minus another integral. Okay? Take a second and work on that. Just set it up, don't solve it. Okay, so yes, these can be simplified. Don't forget the pi. You can simplify and expand, and and some teachers will go ahead and tell you to do this all as one integral. It would be the upper guy squared minus the lower guy squared. And the only advantage to doing that would be that some of your terms might simplify. Okay, you might be able to subtract off some stuff. But let's be realistic here. By the time we start doing these, your ability to do an integral isn't in question. What's really in question is, can you set it up? Now, on the IB exam, these questions would fall in on paper 3, in which case you would have a calculator. Okay. So just for giggles, let's go ahead and do this in the calculator to say that we know how to do it in the calculator. So go ahead and turn it on. Integral from 0 to 2. 4 minus x squared dx minus the integral 0 to of x minus 2. And I'm just going to go ahead and put it to the 4th power, because that's what those exponents are going to simplify to. Right? And we get some nice little value. 32 over 3. And then please don't forget to multiply it by pi. Okay? If I wanted it expanded, you could multiply through by pi and you'd get a slightly different number. But realistically, you can leave it like that as 32 over 3 times pi. Are we good? All right. All right. So if we decide to revolve about something other than the x-axis, then let's take an example of what I'm talking about. We wanted to revolve a function y equals 2 minus x squared, but we want to revolve it around the line y equals 1. Okay. Now, again, you need to think about visualize in 3D what this thing will look like when it's spun around the axis. What do you think it'll look like? Now remember, we're spinning it around the line. Yeah, we're spinning it around this axis. Yeah, it'll actually look a lot like a football. See what I mean? Okay. All right. So again, you want to think about. Well, first of all, there's two ways of approaching this. One, you can think about upper minus lower. Okay. Your upper minus lower, your upper curve. Think about that rectangle. And this right. Your upper is your curve, 2 minus x squared. Minus the lower. And now we square it. And we're going to go from this bound, which is going to be what? 1 and negative 1. Negative 1 to 1. Okay, so I have taught this several times now. It's not my first rodeo. And I will tell you that students totally goof this. The reason why students totally goof this is because they're thinking, well, which one is my upper, my lower? Why am I subtracting them now and then squaring, whereas before I was squaring and then subtracting? Do yourself a favor. Don't even bother. Think about it slightly differently and you'll come up with the same integral. If I took this function, the original function, and I went ahead and translated it so that it's not spinning about the line x equals y equals 1 anymore. If I just move it down, now I'm spinning around the x-axis, aren't I? You know what I mean? So what I'm going to do is I'm going to take this function that I already know, 2 minus x squared, and translate it 1 unit so that I'm not worrying about, I'm spinning around this other weird axis. We just do whatever translation we might need in order to get it so that it is around the axis. And then when we spin it, so now this is this, and really what we now have is 1 minus x squared, right? Still the same bounds as the original one that we talked about. Okay, so don't get all bent out of shape on it. Make a new function that does go around the x-axis so that you're not, doing a whole heck of a lot of work. Okay? Question. What, this graph? Yes. Yeah, this is the football looking shape that once I take that parabola and I spin it around the axis, it's going to look like an oblate spheroid, actually a prolate spheroid. It's going to look like a football. Question. Where's the pie? Oh, missed the pie. Where's my pie? Don't forget the pie. It's like the sea. It's elusive. You forget about it. Okay? It's not so bad, I hope? Okay, good. Okay. By the way, just for the record, this method is sometimes called the washer method. And the reason why it's called the washer method is because when you take that rectangle and you spin the rectangle, it looks like a washer. Okay? Lousy. It gets that washer look to it when it's spun around. Okay. All right, good. Last thing that we need to care about is spinning about the y-axis. Okay. Only thing that's going on here, now I'm just going to go back to the equation that we had before, where it was y equals 4 minus x squared. This was 2, that was 4, 0. Okay. Now, I'm going to spin around the y-axis rather than the x. What's it roughly going to look like when it's spun? What? I have no idea what that is. Oh, yeah, almost half of a football. Almost like, look like a tip of a bullet, something like that. Okay. And in fact, I'm going to go ahead. Oh, there it is. Like, could be the tip of a different mushroom. We've all seen mushrooms that are long and thin like that, or the tip of a bullet or the tip of a shell, kind of a thing like that. Okay. All right. Now, do you expect it to have the same volume? The one when we spun it around the x-axis? No, it will not have. A very, very strange coincidence it was. Okay. Well, it has the same. It has a different cross section. Okay. It's made from the same shape, but let me give you an example that would probably make it clear. Let's say I took that rectangle. Okay. Long, thin, narrow rectangle, and I spun it around the x-axis. I would get a big disc, right? Ooh, ugly. Sorry. I'm no artist. I would get some big looking disc like that, right? That would have a lot of volume. But if I spun it around the y-axis, I'd just get a cylinder. Okay? Well, they would both be cylinders, but one would be very small. Okay. So now when we do this, again, you're going to think about the idea of that rectangle. That rectangle now goes like this. So the trick here is to not deal, is to remember what your integral is going to look like. It's not going to have a dx anymore. It's going to have what? dy. Which means your function needs to be now in terms of y rather than in terms of x. So what you're going to have to do is you're going to have to take roughly the inverse of this. You're going to have to solve for x. Okay? So x squared is equal to 4 minus y. X is equal to the plus or minus square root of 4 minus y. Now, which one do we want, plus or the minus? The plus. Now, quite honestly, it's not going to matter in this example, because even if we chose the negative one, we're still spinning it around the axis. The negative one is going to be this guy back here. And if we spun it, we would still get the same shape, right? If we were spinning the full 360. Okay? Now, later on, you might care about, well, what happens if we don't spin it 360, if we spin it some other angle value? Then we're talking about something that's best dealt with in terms of what's called cylindrical coordinate systems, rather than this system. But you can do it. So we're going to go ahead and take square root 4 minus y squared. Now, what are my bounds this time? Right. Because I'm going from here up to there. That's where we're integrating from. So my lower bound is 0, my upper bound is 4, and it's a straightforward integral at that point. And you can imagine that there's the last case, which is the this is, by the way, this is sometimes called the shell method. You're using layers of shells, but okay. No, this one is the shell method. There is another shell method. We don't have to go into it. All right. Finally, would be, let's take these curves that we dealt with before. 4 minus x squared and x minus 2 plus 2 squared. Okay? And we're going to spin this guy around the y-axis. Again, you're going to think about it the same way. You've got an outer shell, an outer surface, okay? And you're going to bore out the inside of it. And you're going to find the volume of what's left. Okay? Once this guy gets spun, it's going to have a hole in it. Okay? Almost like the classic shape of a beehive. See what I mean? With a hollowed out interior. So again, you think about doing this as two separate integrals. You're going to set this up from 0 to 4. Your outer curve. Now, it needs to be first turned into a form, not in terms of x, but in terms of y. So this guy, we found out was x equals the square root of 4 minus y. And this guy is x equals the square root of y minus 2. Now, be careful. Let's actually do that work right here because we have to be concerned here. Let's do that. Y equals x plus 2 squared. Now, solving for x, plus or minus y equals x plus 2, x is equal to negative 2 plus or minus y. Which one do we want, the plus or the minus? But remember, what does 2 minus y look like? Oh, sorry, I'm missing a square root. 2 plus or minus square root of 1. Hello, Ronto. Which one do we want? Yeah, we do want the minus. Because the minus case is this one. Whereas the plus case is that. All right, that's your lunch. We'll come back to this after. We'll pause for a commercial break. All right, so let's get back to it. Now that everybody's had their lunch. So the outer curve is 4 minus x squared. And just to say that we can do it, we can write this as a single integral, the second one. And we're going to pick negative 2 minus square root of y squared. What? There's an error. Make sure that we put that in the right term. Everything has to be in terms of y when you're integrating up and down. Remember, it's upper minus lower, outer minus inner. Okay. How do we feel about all this? Because the upper curve, sorry, the positive square root is that one. And the lower, that one would be minus square root. We want that side. Anybody have any questions on any of this before we let it dead? No. You have to do it in terms of y. Because we're integrating up and down. Right? Our bounds begin from the bottom to the top. So our values wouldn't give me the, well, we did it in terms of x's. We would be integrating from left to right. We want to be integrating from bottom to top so that when we spin, we're spinning, around the y-axis rather than around the x. All right. This episode of The Ronco Show has been brought to you by the Disc and Washer Methods. And the number 4. And dots.